Hello and welcome to the fourth lecture on permutations and combinations. In the previous lecture, we've looked at some starting concepts for permutations and combinations, such as the concept of n factorial, the concept of NPR, and the concept of NCR. I remind the viewer that n factorial is the number of ways of arranging n distinct objects. NPR is the number of ways of selecting R objects from n distinct objects and arranging them, and NCR is the number of ways of selecting R objects from n distinct objects, where you don't care about the arrangements of those objects. So let's look at some related concepts which are based on these three quantities. So the first concept is the number of ways of selecting at least one object from n distinct objects. So instead of just selecting a specific number of objects from n distinct objects, we are concerned with the number of ways of selecting at least one object. So the total number of ways of selecting at least one object is the number of ways of selecting exactly one object from n distinct objects, which is NC1, plus the number of ways of selecting exactly two objects from n distinct objects, which is NC2, and so on till NCn. So this is the number of ways of selecting at least one object, where at least one is enforced here, where you can't select 0 objects from n distinct objects. And so for the viewers of the chapter on the binomial theorem, this sum should be familiar, where this should be nothing but 2 power n minus 1. So for those of you not familiar with this binomial identity, I refer you to the chapter on the binomial theorem. So far we've only looked at the number of ways of selecting objects from distinct objects, whereas the number of ways of selecting R objects from n identical objects is just equal to 1. It's because if you want to select R objects from n identical objects, you just select R of them, and they're all identical, so it doesn't matter which set of R objects you select, and so the number of ways is just 1. So from this you can deduce that the number of ways of selecting at least one object from n distinct objects equals n, because there's one way of selecting one object, sorry, not n distinct objects, but it's n identical objects, which is what we're concerned with right now. So from the previous result, we're concerned with the number of ways of selecting at least one object from n identical objects, and so this is just n because there's only one way of selecting one object from n identical objects, there's one way of selecting two objects from n identical objects, and so on, and there's only one way of selecting n objects from n identical objects, and so that sum gives us n. A slight generalization of this is the number of ways of selecting at least one object from n distinct objects where n1 objects are identical of type 1 and two objects are identical of type 2 equals n1 plus 1 times n2 plus 1 minus 1. So we assume that n equals n1 plus n2. So set of n objects is divided into two types, where we have n1 objects of type 1 and n2 objects of type 2, and the objects of type 1 are identical to each other and the objects of type 2 are identical to each other. So the number of ways of selecting at least one object from these n distinct objects, not distinct, n objects is n1 plus 1 times n2 plus 1, and you subtract 1 for the case when you don't select any object. And so you can arrive at this result by noticing that n1 plus 1 is the number of ways of selecting at least 0 objects from n1 identical objects, and n2 plus 1 is the number of ways of selecting at least 0 objects from n2 identical objects. And so the product of these two is going to give you the number of ways of selecting at least 0 objects of type n1 and at least 0 objects of type 1 and at least 0 objects of type 2 from n1 and n2 objects of those types respectively. And we've got to subtract 1 for the case when you don't select any object from each of these types. And so that gives you n1 plus 1 times n2 plus 1 minus 1. So let's look at the number of ways of dividing objects into a specified number of groups. So for instance, the number of ways of dividing m plus n plus p objects which are distinct into 3 unequal groups containing m, n, and p objects. So we look at the reason why we specify that the groups have to be unequal, and so that has got to do with the fact that if the groups are equal, then one arrangement in those groups is going to be the same as a rearrangement within the groups themselves, where some of the objects, some of the distinct objects in the which were earlier in group 1 are now in group 2, and some of the distinct objects which were earlier in group 2 which are in are transferred to group 1. And so that rearrangement within the groups themselves is not going to result in a distinct division of these objects into those groups. So we look at that in a minute. But if we consider that the 3 groups have to be unequal, containing m, n, and p objects, then the number of ways is just going to be, so you first have to form a group with m objects, and for that you choose m objects from m plus n plus p objects, and so that can be done in m plus n plus p choose m ways by the definition of NCR. And so now you have n plus p remaining objects and you want to form a group with n objects, and so that can be done in n plus p c n ways. And finally you have p objects and you need to form a group in with p objects, and so you can choose those p objects in PCP ways, which is essentially just one way. And so from the fundamental principle of counting, total number of ways is just the product of these 3 quantities, and you can simplify this result and it will turn out to be m plus n plus p whole factorial divided by m factorial times n factorial times p factorial. So that's going to be the number of ways of dividing m plus n plus p objects which are distinct into 3 unequal groups containing m, n, and p objects. So we'll look at the consequences of the assumption that this was into 3 unequal groups. So what happens if groups are now equal? So let's generalize this result a bit for the case of equal groups. So the number of ways in which mn distinct objects, where Mn is m times n, Mn distinct objects can be divided equally into n groups. And so now we want to divide Mn objects equally into n groups, and so each group will have m objects. So in a manner similar to our previous result, we can just derive this as Mn C m, where you first choose m objects from Mn objects to put in the first group, and then you multiply that by Mn minus m C m, and so on, till finally you only have m objects and you got to choose those m to put in the last group. And so this is going to be the result, where we have so far ignored that the groups are equally divided, where each group has m objects. So if you derive this result out, it's going to turn out to be Mn factorial divided by m factorial whole power n. So far our derivation has been similar to the previous case when we had 3 unequal groups, but now we have n equal groups. So since we have n equal groups, notice that the ordering between the groups themselves shouldn't matter, since we haven't specified that the groups are distinct. So we don't care if there are m objects of, so suppose we have the first arrangement to have, say, A1, object A1, A2 till AM in group 1, and object B1, B2, so on till BM in group 2, and so on. There's some other objects in the other groups, we don't care about those. So another arrangement according to this selection would be B1, B2, BM in group 1, A1, A2, AM in group 2, and the same arrangement that we had in our previous arrangement 1. So the rest is just same as 1. So these two arrangements will count differently in this scenario, since choosing the different m objects from the Mn objects and choosing the original m objects from the Mn minus m objects is going to count as a different division. So we don't want to count these two as different divisions, because they are essentially the same division of objects into these groups. So to counter this, to discount for these different arrangements, we are going to divide by 1 over, we are going to multiply by 1 over n factorial. This n factorial comes from the fact that we have these n groups, and these n groups all have the same number of objects, and the ordering between these groups themselves, the label which we are giving to these groups doesn't matter. So that's why we are discounting the n factorial in this case, and that is the distinction between this case and the case when we had m plus n plus p factorial divided by m factorial times n factorial times p factorial. So that's the relevance of the assumption that the groups are unequal in this case and that the groups are equal in this case. So let's see some examples of these results which we've looked at. So the first example is going to be, so suppose person A has 5 friends. So how many distinct groups of friends can he invite to a party so that at least one friend is invited? So A wants to throw a party, and we want to invite friends for the party, and he wants to look at the total number of ways in which he can invite at least one friend to the party, and the number of different ways in which he can do this. So this result is just going to be the number of ways of choosing at least one object from 5 distinct objects, since all friends are distinct. So this is going to be NC1, sorry, 5C1 in this case, and so on till 5C5. And from our first result that we've seen today, this is going to be nothing but 2 power 5 minus 1, which is 31. So there are 31 different distinct groups of friends he can invite to the party, so that at least one friend is invited in each. So let me just erase this portion to make more room for our second example. So second example asks us to compute the number of factors of the number n equals a power 7 times b power 4 times c cubed times d times e times f. So n is this product of these numbers raised to these exponents, and a, b, c, d, e, and f are prime numbers. So you're required to compute the number of distinct factors of this number, and you can assume that a, b, c, d, e, and f are all distinct. So the way to approach this problem is to notice that this is essentially a problem based on choices of these prime factors. So each divisor of this number is going to be, a generic divisor is going to be of the form a power alpha 1 times b power alpha 2 times c power alpha 3 times d power alpha 4 times e power alpha 5 times f power alpha 6, where alpha 1 is a number which is between 0 and 7, both included. Alpha 2 is a number between 0 and 4, both included, and alpha 3 is a number between 0 and 3, both included, and so on. So you can consider this problem to be the case when you have 7 objects of type 1, 7 identical objects of type 1, because all of the factors corresponding to a power 7 are all identical. They're going to be 1, a square, a cube, and so on till a power 7. So you have 7 identical objects of type 1, you have 4 identical objects of type 2, you have 3 identical objects of type 3, and so on, and you have 1 identical object of type 6. So you can consider this problem to be equivalent to that problem. And we've seen here the number of ways of selecting at least one object from n distinct objects, where n1 objects are of type 1 and n2 objects are of type 2, and so on. So by a generalization of this result, the number of ways is going to be number of factors, or the number of ways is going to be 7 plus 1, where the number of ways of choosing at least 0 factors, at least a 0 exponent for a, times 4 plus 1, where this 4 plus 1 is the number of ways of choosing 0, 1, 2, 3, or 4 for b, for the exponent of b, times 3 plus 1 corresponding to c, times 1 plus 1 corresponding to d, times 1 plus 1 corresponding to e, times 1 plus 1 corresponding to f. And note that unlike the previous case, we are not subtracting 1 for the case when we don't choose any, a power of any of the prime divisors of the number n, and that's because we allow 1 to be a factor of this number n itself. So you can evaluate this result. This is nothing but 8 times 5 times 4 times 2 cubed, which is again 8. And this is nothing but 64 times 5, which is 320, times 4, which is 1280. So the number of factors of this number n, which is given in this form, is 1280. And note that in this computation we've included both the factor 1, where we choose a 0 exponent for each of these prime divisors of the number, and we've also included the factor n, where you choose 7, 4, 3, 1, 1, and 1 for each of these corresponding prime factors of the number n. So we've included 1 and we've included the number n themselves in this count of the number of factors of this number n. And if you wanted to discount those factors, you can just subtract the corresponding number that you want to discount in your computation. So that's it for this lecture. I hope you enjoyed watching this lecture on permutations and combinations, and in our next lecture we will be looking at the concept of circular permutations. Thank you for watching.